We will now turn to containers. As I said before, informally, you can think of containers as containers that contain a collection of other things, like, for example, primitive data types. The most simple container we can think of are lists. Lists are created by using the square brackets, and lists can contain an arbitrary collection of primitive data types. So, for example, we can create a list that contains the integer 1, the float 4.5, the string hello, and the Boolean value true. If we execute this, we see here that x is of type list, and if we look at x, we actually see that it contains exactly what we just defined it. A list can really contain an arbitrary number of primitive data types, and they do not need to be of the same type. In fact, you can even actually create a new list that contains, for example, the float 1.0 and that contains x as an element. So containers can also contain containers. If you look at y, you actually see here that we now have a nested list structure. You can do things with containers that you cannot do with or that do not make much sense for primitive data types. So, for example, you can ask Python about the length of a list using the function length. If you pass x as an argument to the function length, then length tells you the length of the list x. If you want to access certain elements of lists, you can do this by supplying the corresponding index. To do this, there are two important things in mind. So, for example, what do you think do you need to type here if you want to access the first element of x? If I tell you that you can do this by supplying the index within square brackets. Now, what I naturally would actually think that I need to type x and provide the integer 1, yet it actually turns out that that Python does not start counting at 1 with regard to the indexes, but Python starts counting at 0. So if you want to have the first element of a list, you actually have to use the integer 0. Also keep in mind that you need to supply indices always as integers, not as floats. And naturally, the next question is actually what kind of operators you can use with lists. As with strings, it does not make much sense actually to use the minus operator with lists. That is unsupported. But what is often useful is actually to add one list to another. As with strings, this basically concatenates the list into a new, longer list. Also, you can multiply lists, which basically means that the list gets repeated over and over again. The next container we look at are the so-called tuples. It's best to understand tuples if they are compared directly with lists. So let us create a new list here that contains the numbers 1, 2, and 3, and then create a tuple that also contains the numbers 1, 2, and 3. You create a tuple almost in the same way as the list, but by using normal brackets and not square brackets. You might now ask yourself, what is the difference between a tuple and a list? What you can do with lists is actually you can mutate them. So for example, if we want to change the second element of the list L, what we can write here, we can access the second element by supplying index 1, and we can provide here a new element to be associated with the second index of L. If we print this, we see that we have replaced the second element of L. Let's try to do this for the tuple. This actually doesn't work. This is actually the most important difference between tuples and lists. Lists are mutable, tuples are not. If you have very large lists, you might wonder whether a certain element is actually in a list or not. You can then ask Python by writing, for example, 2 in L. This basically asks Python, is integer 2 an element of list L? If you execute this command, then Python will give you the answer. 2 is obviously not an L anymore because we have replaced the second element here with 9. So if we look at the list, we see that it contains 1, 9, and 3, but 2 isn't in the list anymore. In order to create a set, we need the set function. So let's create a set that we call set1. We use the set function, and the arguments of the set function must not be single elements, but must be so-called iterables. We will learn about that later, but for now we can simply supply a list. So for example, we can supply the list, this list here. If we look at the set, we actually see that sets are printed within these curly brackets. And we also immediately see that one important distinction of sets with regard to lists. If you supply an element more than once, it is automatically eliminated because sets cannot contain duplicate elements. Another important difference is that the order of the elements of sets is not fixed. For example, if we look at this list, it has a particular order. And if we transform it into a set, then we actually see that the order of the elements here has changed. And that is because the ordering of the members of a set is not fixed and it doesn't have any meaning. Because of this, also indexing in sets does not work because it doesn't make any sense. It does not make any sense to ask Python about the first element of a set. So Python informs us about this by throwing a type error and telling us that a set object is not subscriptable, which basically means we cannot use indices to address certain elements of a set. What we can do, just as with tuples, is we can ask Python whether a certain element is in a set. We do this with a keyword in, just as before, and we get a Boolean value as a response. It is also possible to ask Python about the common set theoretic operations, like to ask Python for the difference, the union, the intersection, and the symmetric difference between the sets. If you want, you can just try to find out how that works. If not, you can also look it up in the scripts, or we can do it together. To solve this exercise, we first define the two sets as discussed before, by writing the set elements within curly brackets. We can now verify that these two objects are actually sets and then proceed to the actual computations. We first search for the difference between set A and set B, and this is basically the set containing the elements that are in set A but not in set B. To calculate this in Python, we just use the minus operator. And we have a look. If we are interested in the elements that are in set B but not in set A, we just have to write it the other way around. So we can proceed to the next step. The union is the set that contains all elements that are either in set A or in set B or both, and we can get the union of the two sets by using the pipe operator, not the plus operator. So as we can see, these are the elements that are either in set A or in B or in both. And we can then next proceed with the intersection, which is the set that contains those elements that are both in set A and set B. And we can get this in Python by using the AND operator. So we are only missing the symmetric difference, which is the set of elements that are in either of the two sets, but not in their intersection, and we get this by the head operator in Python. So, and that's basically it. With these operators, you can get all the common set theoretic results. There are also a couple of more, less common, which you can look up in the internet, but I think with this, you already very well prepared for what's to come next.